Hello, everyone. Hope you're doing well. Gonna wait about one more minute for some more people to join. All right, so I think I'm gonna start. I want to remind you that you have about 2 days left to finish your midterm if you haven't taken it already. Okay, so we are moving on from forces today, and our next topic is called energy. Energy. Okay, so energy is basically it's a number, and it's a number that basically tells you what can happen and what cannot happen. Okay, so if you want to do something, you have to have enough energy to do it. Okay, so it's a nice way of looking at the world. Okay, so um, so I'm not even going to bother writing down the definition right now because it's kind of abstract. So we're just going to start off by talking about some different types of energy. Okay, and so there are probably the most fundamental type of energy is what's called kinetic energy. And kinetic energy is the energy of motion. Okay, so in order to have kinetic energy, something must be moving. Kinetic energy is denoted by K, and the formula for kinetic energy is 1/2 times the object's mass times its speed squared. Okay? So this is the formula for kinetic energy. So you can see why it's called kinetic energy, because it depends on the speed. The more speed you have, the more kinetic energy you have. So this is probably the most fundamental form of energy. Okay? Another form of energy is called potential energy. So a potential energy is basically an energy that you have due to your position or due to your configuration. So it has to do not with how fast you're going, but just like the organization of the thing has to do with potential energy. So it's the energy of position. And there are multiple types of potential energy. There could be, for example, chemical potential energy. Chemical potential energy is the energy of For example, gasoline. The gasoline molecules have a certain configuration that gives them energy. There's electrical potential energy. That's the energy that you have in a storm cloud before a lightning strike. But the type of energy that I'm going to discuss with you today is called gravitational potential energy. And that is the energy due to position in a gravitational field. Okay, so because you are in a gravitational field, you have gravitational potential energy. I'm going to denote any form of potential energy by the letter U, and then I'll put a subscript there to indicate which type of potential energy it is. So U sub G for gravitational. And the formula for gravitational potential energy is mgy, where y is the elevation of the object. So something has more gravitational potential energy the larger its elevation. If you move something from side to side, you're not changing its elevation, and so therefore you're not changing its gravitational potential energy. You move it up, you're increasing its gravitational potential energy. You move it down, you're decreasing it. Okay? Now this formula is a little bit ambiguous because elevation relative to what? Elevation relative to Claremont, elevation relative to sea level. And it turns out that you get to define where y equals 0 is. Okay? So you get to define the zero of gravitational potential energy, and it's not going to affect the result of the problem. Okay? So for example, what if I put y equals 0 right here? Okay? And then I have three objects. I have object A, I have object B, and I have object C. Object A has a positive gravitational potential energy because it's above y equals 0. Object B has 0 gravitational potential energy, and object C is below y equals 0, so it actually has negative gravitational potential energy. So it's totally fine to have negative gravitational potential energy. That's okay. However, what if I redefined y equals 0? And now what if I said this is y equals 0? I'll call it y squiggle equals 0. In that case, all three of them are above y equals 0. Okay. So they all have positive gravitational potential energy. So where you define y equals 0 is going to affect the numerical value of the gravitational potential energy, but it's not going to affect the result of your calculation. Okay? So you just, typically speaking, I'll just choose y equals 0 to be the floor. Okay? M is, of course, the object's mass, and g is the acceleration due to gravity. There's another form of energy that we're not going to discuss too much, but it is very important, and that's called heat or thermal energy. And that is the energy. So what is heat? If you're hot, what does that mean? It's the energy of random atomic motions. So it's almost invisible. You can't really look at something and tell if it's hot or not unless it's so hot that it's glowing. But um, uh, any material is made up out of atoms, and those atoms are bound together, and they're all kind of jiggling in place. Those atoms are all jiggling, bouncing around, and sort of the thermal energy is the amount that basically how violent that jiggling is. Okay, if something is incredibly hot, then that means that the atoms are really moving around quickly in place. Okay, atoms are never going to be completely at rest. They're always jiggling just a little bit. Okay, so that's an important form of energy. It's kind of like once energy is transformed into thermal energy, it's really hard to recover it again. Okay, so we'll talk more about heat as we go on in this course. So there is something called the total mechanical energy. Okay, the total mechanical energy. And all right, so the total mechanical energy is denoted by E, and it's equal to an object's kinetic energy plus its potential energy. All right, so we're not including heat in this, but okay, but we are including kinetic and potential energies. So you add the two of them together. All right, let's do a quick example of calculating. Oh, I haven't given you the units of energy. So the units of all forms of energy. So the units of kinetic energy, the units of potential energy, the units of thermal energy. It's called the joule, Joule, which is denoted by J. All right. The joule. All right, so let's do just a little example here. I'm going to draw it over here, actually. So what if we have, here's the ground, and we have a bird that is flying, okay? Here's the bird. The bird's flying, and the bird has an elevation of 11 meters relative to the ground, so I'm just calling the ground y equals 0. It's flying with a velocity of 5 meters per second, and we'll say that the bird has a mass of 1 kilogram. Okay, so what would be the total mechanical energy of the bird? Well, this bird is elevated, and so it has potential energy. Okay, and the bird is moving, so it has kinetic energy. So the energy is going to be 1/2 mv squared plus mgy. So plugging in the numbers, 1/2 times the mass, which is 1, times the speed, which is 5, and I square that, plus m, which is 1, times gravity, this is a bird on Earth, 10, times elevation, which is 11. Okay, so that's 110, and this is 12.5 So that's going to be 122.5 joules. That's the mechanical energy of the bird. Okay? So that's how you calculate total mechanical energy. And if you had more than one object, for example, you had two birds, the total mechanical energy of that system would be the mechanical energy of bird 1 plus the mechanical energy of bird 2. Okay? So, what I want to talk about now is something called the law of conservation of energy. Okay? The law of conservation of energy. And this is a really important law in physics. And what it says is that energy cannot be created or destroyed, only transformed. Okay? So the total amount of energy in the universe is staying the same. Okay? But energy is transforming from one form to the other. So, for example, if you take gasoline and you burn it, you're taking the chemical potential energy of the gasoline molecules and you're transforming that chemical potential energy into thermal energy. Okay? If you talk about a solar panel takes the energy of the sun's rays, so the energy of waves, if you will, because light is a wave. So the energy of that wave, and you're converting it into electrical energy. Okay? Energy transforms. If you're going skiing and you're up on the mountain, you're elevated, you have a lot of gravitational potential energy. Okay? You go down the ski slope, you're transforming that gravitational potential energy into kinetic energy. That's why you go fast, as you go faster and faster as you drop. So energy is being transformed, but the total amount is always going to stay the same. So, for example, if you lose 5 joules of gravitational potential energy, then while you're skiing, then you gained 5 joules of kinetic energy. You see how that works? So it's transforming, but the total amount doesn't change. Another way of saying that is by saying that the initial energy is equal to the final energy. So the amount of energy that you start with is going to be equal to the amount of energy that you end up with, but the forms of energy, the balance of different types of energies are going to be different. Okay, so a good example is a great example for energy problems is a roller coaster. Okay, so if you have a roller coaster, maybe the roller coaster is climbing, and here's the roller coaster cart, and it goes up the ramp. And we're not going to worry about, it coasts up the ramp. You know how when you go on a roller coaster and you get on the hill, it's like it latches on and it gets carried up the rest of the way? We're saying that it's just coasting up the hill. So if we think about the total energy of the coaster, it's kinetic and potential. Okay. Right here, it has a lot of kinetic energy and not a lot of potential energy. Okay, but as it climbs, it's gaining elevation. So the potential energy is going to go up, but we can't have the potential energy go up and keep the kinetic energy at the same value, you see? So as the potential energy goes up, the kinetic energy goes down. So there's an exchange, there's a transformation. But the total amount, if we added kinetic plus potential, it's going to be the same. Okay? Let's do an example. And the example is a roller coaster. A roller coaster. Okay, so we have a roller coaster, and the roller coaster cart starts off at rest, and it's at an elevation. Starts off at an elevation of 100 meters, so quite tall. And then the roller coaster goes wee, and it ends up at an elevation of 35 meters. Okay, so that's its final elevation. Starts out at rest, ends up down here. So notice how we went down. So we lost gravitational potential energy. Because that gravitational potential energy cannot just disappear, we had to have gained another form of energy. And so the energy that we gained was kinetic energy. So the question is, how fast is the roller coaster cart going once it reaches that spot, that elevation? Okay? So we're going to use the conservation of energy to solve this problem. Some of you might be thinking, I didn't give you the mass of the roller coaster cart. Okay? And that's true. It turns out that it's not going to matter. And so we'll see why the mass of the roller coaster doesn't matter when we're solving this problem in just a moment. Okay? So initial energy equals final energy. That's the law of conservation of energy. If we look at it, the roller coaster cart begins with elevation. So it begins with gravitational potential energy. Okay? It starts at rest, though, so it does not begin with kinetic energy. So our initial energy is going to be mgy. All right? If we look at the final, okay, if we look at the final elevation, it still hasn't reached ground level yet, so it still has gravitational potential energy. So it's still going to have mgy when it reaches this spot. It's just the y value is going to be different. Okay. And then also, because the y value has changed, it picked up speed. So we now have motion happening. So we have kinetic energy, 1/2 mv squared. All right. So let's plug in some numbers. So initially, so we don't know what the mass is, so I'm just going to leave it as a variable. Gravity is 10. The y value is, to start out, is 100. Okay? In the end, we have m times g times y, which is 35 once we reach this spot. Okay, so it's not 100 anymore. The y value is 35. Plus 1/2 times m times the velocity squared, where v is the velocity at this location. So one of the things we can see here is that each term in this equation has mass. Okay, so the mass cancels out. So the mass of the roller coaster cart, although we couldn't calculate the actual amount of gravitational potential energy, without knowing the mass, but we can still figure out how fast it's going to be going once it reaches here without the mass, because the mass cancels out of the key equation that we use to solve it, okay? So the mass canceled out in that case. It's not always going to cancel out, as we'll see in the next lesson, but for this one it does. So we have 100 times 10 is 1,000. 10 times 35 is 350, plus 1/2 v squared. Subtract the 350 over to the other side. That gives us 650 equals 1/2 v squared. Multiply by 2, 1,300 equals v squared. Take the square root. And we get that the coaster cart is going to be going at 36 meters per second once it reaches that elevation. Okay. Now I'm actually going to redo the problem. Okay. Only this time I'm going to do the problem as if the starting position of the roller coaster was y equals 0. Okay? And I'm going to show you that we still get 36 meters per second. So let's see how that works. So we still have the same equation. We start out with gravitational potential energy. We end up with gravitational potential energy and kinetic energy. Okay? But here's the thing. The roller coaster cart begins at y equals 0. So y equals 0 is the initial energy. Okay? So we actually start out with 0 energy. All right? We end up down here. So notice how if we put y equals 0 right here, we end up at a negative value of y. And we can see that this distance right here would be 65 meters. So we actually end up 65 meters below y equals 0. So we have m times 10 times negative 65. Negative 65 is our final elevation, plus 1/2 mv squared. Okay? I can see that this is negative 650 m plus 1/2 mv squared. Add that term to the other side. 650 m equals 1/2 mv squared. Can see the m's cancel out again. Multiply by 2, I get 1,300 equals v squared. So see how our choice of where y equals 0 will change the amount of energy that the roller coaster has, but it doesn't change the speed once it gets to this spot. So that's why I say you get to choose. You get to choose where y equals 0 is going to be. Okay? Now, a lot of people are sort of blown away by conservation of energy. They say, wow, there's this thing that is conserved. Wow. And the thing I want to stress is that energy is a quantity that is defined by humans. Okay? Humans define energy, and they defined energy in such a way that it is conserved. Okay? So energy is defined to be conserved. Let's suppose, so a lot of times students ask me, they'll say, well, like, could we, produce a, make a perpetual motion machine that produces energy for us, okay? That would appear to violate the law of conservation of energy. But really, if you think that you found something that violates the law of conservation of energy, what you actually did was you discovered a new form of energy, if that makes sense. So whenever a physicist encounters something that appears to violate the law of conservation of energy, what they say that no, it actually isn't violated. We just found a new form of energy, and they add it to the list of types of energy. Okay, so you cannot beat conservation of energy by definition. All right. The other thing I wanted to talk about is, why is energy such a neat thing to be able to calculate with? Well, at no point, think about this problem. At no point did the detailed shape of the roller coaster come into play. All right? The roller coaster could have been shaped like anything. It could have done this and then gone back to that elevation. Okay? The shape of the roller coaster track did not matter. Okay? So it's a very powerful tool. Whereas if we wanted to analyze this roller coaster in terms of forces, it would be much, much more difficult. Okay? We would have a normal force from the roller coaster track. We would have the weight force. And as the roller coaster moves, the direction of the normal force is going to change, which is going to affect its acceleration, and it's just going to get really, really complicated. If we analyze in terms of energy, it's very simple. All right. I wanted to talk about a few more things before I end my lesson. The other thing I wanted to talk about is the calorie. Okay. 1 capital C calorie. So calorie is a unit of energy. Okay. Typically, calories are used to measure thermal energy, but it's just another unit of energy. Okay. The calorie, 1 calorie, is equal to 4,186 joules. Okay. So joules and calories are both measuring energy. You might have heard of the calorie in the context of your diet. Okay, the recommended diet is something like 2,000 calories per day. So what they're saying is the amount of food that you eat should have a chemical potential energy equal to 2,000 calories. Okay. Now, what your body does, if the food that you're putting into your body has more chemical potential energy than you need, your body will store that chemical potential energy in the form of fat. So really, it's all about energy conservation. Okay. So I think that's kind of interesting. Let's see. I think there was one other thing I wanted to say. I'm trying to remember. Another thing I wanted to talk about is energy is kind of like money. So I want to give you an analogy, okay? If you think about money or wealth, there are different forms of wealth. You can have a house, you could have a car, you could have a banking account, you could have a checking account or a savings account, you could have stocks, you could have cash. So all these different forms of wealth, but the amount of wealth is constant. You can transform one form of wealth into another form of wealth. So, for example, you could transform the wealth of a stock into wealth in the form of cash by selling the stock. That's transforming it into a different form of wealth. Okay. You could then take that cash and buy a house, and so you're transforming that wealth into the form of a house. So just like the types of wealth that you have can be transformed from one form into another, energy is transformed from one form to another. Okay? So I think that's a useful way to think about it. All right, well, that's my lesson for today. So I will see you in the Zoom room. Bye for now.